Alrighty, guys. Can you hear me again? Alrighty. So I got my computer charged again. Let's just quickly go over this. Right. So the goal is to calculate the replicating portfolio at theta. And as you saw on the previous slide, that involves computing a derivative, right? If you want to compute the replicating portfolio in the Black-Scholes formula, this here is related to the replicating portfolio using that formula we had from one of the previous slides. It says that you have to compute the derivative of the call price, right? So that's what we have here. This is this object here. This is my theta zero. Let's equal to this. And so we're going to look at where we discussed the re-simulation, where you just look at simulating this expectation here for two different values of S0, and then looking at the difference and dividing. That's not a good idea. There's a classic paper by Brody and Wasserman, which has a number of suggestions on how to do it in Black-Scholes. And we're going to look at two. So we're going to look at this one and then one more. The first one is what they call a pathwise derivative. You observe that the stock price is linear in the initial value, so it's straightforward to compute the derivative. It's just the slope. It's this random variable here that's the slope, and so if you play the game, you can realize that this derivative that we're interested in, it's given by nothing else than an expectation, which you already know how to do. The only difference is that instead of computing the expectation, instead of approximating the expectation of the calls payout, you have to approximate it for this one here. So that was one way of doing it, and that's what they call a pathwise derivative. The second way that you suggest to do it is called the likelihood ratio. So Brody and Klasserman, he also suggests the likelihood ratio. So what is that method about? Well, you say write this expectation that you're interested in terms of the density, right? So write this expectation here as an integral over the density. So write it as an integral, say, over R x minus k positive part g of x dx, where g is ST's density under that Q measure. So let's write out what that is. All right, so we have Q of ST less than X. We're in Black-Scholes, so this is Q of S0 E sigma BT Q minus 1/2 sigma squared T less than X. Okay, so we need a derivative here with respect to X to get the density. And this is my G of X. What are we going to get? We're moving S0 on the other side, X divided by S0, taking log. We're going to get sigma BT Q minus 1/2 sigma squared T. I want to get a standard normal, so I'm going to normalize by, what would it be? Sigma square root T. This will be Q. So on the other side, I'll have log x over s naught plus 1/2 sigma squared t. I want to normalize by sigma square root t. So this leaves me with bt q divided by square root t. And I want to use this one here, standard normal. Mean 0, variance 1. So I can write everything here as the derivative with respect to x of the normal distribution evaluated. So this n and that n, they're not the same, right? This one here is the normal distribution. This is x over s naught plus 1/2 sigma squared t sigma root t. All right, so here n of a, it is 1 over root 2 pi integral from minus infinity to a e to the minus y squared over 2 dy. So if I want to compute the derivative, I need n prime. So this would be n prime, evaluated all that mess there. Log x over s naught. That's 1 over 2 sigma root t, and then multiply by the derivative of what's inside. This is what would be 1 over sigma root t, and then log, this is 1 over x. This is true for x positive, right, and 0 otherwise. And of course, n prime here. This is 1 over root 2 pi e to the minus a squared over 2. So if we want, we can also plug in what n prime is. Let's just keep it like this for now and see how to use it. That's my derivative. So if I'm interested in, that's the value of the derivative. I'm interested in the derivative with respect to the initial value. So let's see how to do that. I will then need to compute a derivative with respect to S0 of that expectation. Of this expectation. Divided over here in the density form. I need to compute a derivative over here of x minus k plus g of x dx. And so if I move the derivative inside as before, again, we're being sloppy here, but now the S0 is over here in g, right? We see that from the calculation. That's it. The g that we're computing, the density function, was the derivative. We go all the way back down here, and you see this is where S0 is. S0 is in there. There's no other S0, right? So it's right, it's hidden right there. So we move the derivative away from the payoff, and then we put it over here on the density. And we can then recall, if we take the log, take the derivative with respect to S0, let's say log of g of x. This is 1 over g of x, and then the derivative with respect to S0 of g of x. So we can express this derivative here in terms of the log. So we can write this here by writing an integral over R. And again, the density here is 0 on the negative part. I'm just writing it to G. Like this works for x positive. So it's equal to that, and it's equal to 0 when x is less than or equal to 0. Whether integrate over R or integrate over the positive ones, this is the same because G is equal to 0 on the negative part. So if I insert here, I will get this would be x minus k positive part. And this derivative here is what I have over here. I move G on the other side. And then the derivative with respect to the log of G of x dx. And now what we recognize is that here, this is a density function. So we're integrating again with respect to the density, and we can write everything here as an expectation under the West-Neutral measure of a payoff of st minus k positive part. G is the density, so that becomes the expectation, and then there's a derivative. I need more space here, I can't fit it. Can't fit it, I need more space. It becomes an integral over R, x minus k positive part. So this was the expectation. And G, that was the density, gets into the expectation, and then we have the derivative with respect to this 0 log of G of st. So again, what we see is this is just another payoff. This is just another function of st. So you can use, just as before, the pathwise derivative, you're able to write the derivative in this form, right? But that's just another function of st. So if you know how to do this one, you'll know how to do this one. It's just a different function. And likewise, what you see here is this is yet just another function of st. So if you want to compute the derivative, which is needed to get the initial value of the recurrent portfolio, you have to be able to compute this expectation, but that's just an expectation of a function, and you can simulate it. Right? You have what G is. G is actually very nice when we apply that log to it. Like this n prime that you have here, has to do with the exponential function. So you have the exponential function, and then you have a log here. So it all works out very nicely when you compute this. I don't want to do it. It's I can show you the formula. It's a mess of a formula, but there's nothing difficult about it. You just compute this derivative, and you're going to be fine. So these are the two methods that Brody and Glasserman suggested. There are other ways of doing it too, but these ones here in the Black-Scholes world, you're standard. Are there any questions or comments on how to do one of these two? Okay. Then let's go back and look at where we are. We did the replicating portfolio, and this took a long time. this one here is for the next homework number 4. So the next one is homework number 3. We already talked about Heston and Steiner-Stein's model. So let me push this here to next time. You won't need it until homework 4, which is weeks away from now. This will give you some time to think about the notes that we had today about Heston's model. We've done a lot of stochastic calculus already related to PDEs and Newton's lemma. Let me redo some of that next time for Heston's model, go over some of the things again, but let me apply it next time to characteristic functions, which is what you need for homework number 4. The Cox processes, this is a little bit less involved in terms of stochastic analysis, and there's we already been at this for a couple of hours, so maybe doing something that is a little bit lighter here at the end is easier. So let's talk about Cox processes and CDS contracts. It is less math heavy than the first part, and then we'll do this next time, and couplers will come next time as well. So let's talk a little bit about CDS contracts. So credit default swaps. They were very, very popular. Very, very popular in 2000, I'd say 2005 to 2008. I mean, at that point, they were. There's going to be an underlying. There's an underlying entity. There's an underlying name. There's an underlying name like Microsoft or your favorite. Or your favorite country, state, or company. It could be Microsoft. It could be Greece has been subject to this quite a bit. And states, US states, or some company that you're interested in, there's an underlying name which can default, which can default. Default here you should be a bit liberal about the meaning of default. It is more like a credit event, in particular in terms of a country like Greece. It's a credit event. It could be a debt restructuring. It doesn't have to be default. The contract will specify like a number of these things. Like Russia defaulted at some point, so it could also be. Don't mean to single out Greece here. Russia had a default. The US has been very close to defaulting a number of times. That happens when Congress can't agree on extending the debt ceiling. Like the US debt is in what mid 20 trillions, and then it has to be extended on a regular basis. And sometimes they're having a hard time agreeing on how to proceed. And if and when they can't agree, well, then the US is going to default on its obligations, and so the US could also be in here. The US is a little bit different because a lot of the debt of the US is issued in dollars, whereas Greece, for example, would have their debt issued in euros, but Greece doesn't control the euro printer. The US controls the US dollar printer. And so that's the difference. Greece would not be able to print its own money and then repay the debt. So there are differences here. So we have an underlying name, it can default. Okay, so then you place a bet. You place a bet. Place a bet on this happening, on default. You place a bet on default. Place a bet on default over over a horizon. So it could be like 1 month, it could be half a year, it could be 1 year, it could be 5 years, it could be whatever you can agree on. So you take a bet, short or long. So this here could be short or long. Right, you can take one side, take the other side, and then if default happens, you get this 1 minus pi times the notional. That's the notional is what you put down. Let's just say that this thing here is equal to $1. And then there's this weird construction here in the front, this 1 minus pi. This here is called recovery. This is how much. Ideally, this is how much the company or the name pays or is worth. How much it pays itself. These contracts started out by saying that originally these CDS, they were meant to hedge. We were meant to hedge, say, bond risk. In the sense that you held. So if you held a bond, if you held a bond, you would get pi from the bond and 1 minus pi from the CDS. Right, so overall, you get your $1 back. That was how it was, I think, originally intended to work. You would have to have the bond, and then you will get the pi from the company, and you get 1 minus pi from the CDS. So this then emerged to when the crisis was happening here, just before 2007. Lots of people held CDS contracts without having the bond, and so then you would have crazy situations like, how would this 1 minus pi work out? Well, situations like the following became a problem. Became a problem. Like the way that this 1 minus pi thing worked was that, so if you bought protection, and the default happened, you needed a bond to get you need a bond to get the notional from the CDS protection provider. Right, so if you bought protection, right, you bought insurance, such that if default happened, okay, so that means that guy, he will give you one if you give him pi, or if you give you the bond. So then, why is this a problem? Well, if there are if there are many more CDS out there, then there are many more CDSs out there than there are bonds, then then there's a there can be a shortage. In particular, because unwinding of these CDS positions. So if you wanted to sell a CDS, often, so if you have a CDS and you want to sell it, so if you have a CDS and you want to sell it, you don't sell it, you enter the opposite position. You enter another CDS, of opposite sign. So that means that you still have the CDS on your book, but you just entered one with the opposite sign, and so ideally these should net out. But of course, this involves counterparty risk, because you might not sell the CDS in the sense that you enter the opposite one with the same party that you had the original position from. Right. So when there's a default, all these things has to like unravel, and for it to unravel, everybody has to get their hands on these bonds that have defaulted. And if there are not that many bonds compared to the notional that's out there on CDS contracts, then it becomes a real problem. That means that these bonds that are defaulted, they start trading at very high prices, because all the CDS holders, they have to get their hands on them to collect the fee payments. So at some point, the CDS market outgrew the bond market many folds. And you had this physical settlement, and this was it was just a real mess. And in particular, if you looked at the books that the various CDS dealers had, like you would have this exposure that you have struck CDS contracts with many different other dealers, and you were expecting these payments from these other dealers to come in, but if one of these other dealers defaulted, then you wouldn't get that payment. And that would then mean that they had this exposure, they had counterparty risk exposure. Right, so this is counterparty risk exposure is huge here. There's counterparty risk galore. But this is how the world was in 2005 to 2008. CDS contracts were extremely popular contracts, and it's a bet on somebody defaulting. You can take one of the two sides. Either you provide protection in case of a default, or you gain from it. Right, so in many ways, this is just like an insurance contract, but the big difference is these contracts were not treated as insurance contracts in this period. They were not subject to the same rules and regulations that insurance contracts had. For example, in the US, you were not allowed during this period, and you still are not allowed to take out life insurance, for example, on another person. I'm not allowed to take out life insurance on my neighbor. And it's kind of obvious why, right? Because it creates this dangerous incentive. So we don't allow that. I am allowed with these contracts here to place a bet on the neighbor store going bankrupt. And this was allowed. And it was because one did not consider these as insurance contracts. So then the financial crisis came, all these regulations with Dodd-Frank and so on, all this got changed around. But back then, these were treated as non-insurance contracts, so you were not subject to the same set of rules and laws that insurance contracts have. Like, I cannot take out fire protection on my neighbor's house. I'm not allowed to place a bet on my neighbor's house burning down for obvious reasons. Like, they would give us dangerous incentives. But I am allowed to take out, in this period, I was allowed to take out a bet that my neighbor state, New York, would go default. That was okay. And again, it created very strange incentives. Enron was heavily involved in speculating against on these type of contracts, where they were hoping and pushing the market in their favor by preventing companies, for example, from obtaining the loans that they needed to continue in a non-default state. So there are lots of problems with this, and then of course some of the financial crisis has been attributed to exactly contracts like these ones. Are there questions on the CDS contract before we start doing some math on it? They're endless. These contracts, they were over the counter. You were not traded on exchanges. You were over the counter contracts. So there are two components to them, right? So on one hand, there are two legs, like a standard swap. There are two legs. There's a fee leg. There's a fee leg, right? So you pay the fee. But you pay the fee. So let's say it's a 1 year horizon. And then I don't know how often you pay the fee, maybe every quarter. You pay this fee, you pay the fee till default. There are some that are like a mixture of all upfront and running, and all running fees, in the sense that there are CDS contracts out there where you pay everything up front instead of paying it periodically. So you can think about, again, insurance. How do you pay car insurance? Well, you pay car insurance typically every half a year, but in principle, you could pay car insurance for the rest of your life up front. So you can either have a large payment in the beginning and then smaller, and then no payments in the future. You could have smaller payments in the future and no payment in the beginning. So, and then of course there can be a mixture of them. So that's the fee leg, and then you'll also have the protection leg. And the protection leg, it just pays out if there is a default sometime in this period, right? It'll pay out like 1 minus pi. Pi is typically somewhere around 0.4. That's become the industry standard. So 40% on the dollar. So it pays out in case there is a default, then it'll pay out at that default time. Right. So this is, if you say that is tau, this is the default time. Right. So it pays out if there's default in the window. Otherwise, it pays out nothing. Right. So you get 1 minus pi at time tau. Otherwise, you get 0. So those are the two legs. You pay the fee on a running basis, say, and the way you get the fair spread, the fair fee, the fair CDS fee, this is also called the spread. The fair fee equates the values of the two legs. Just like in a regular fixed for floating interest rate swap, there are two legs there, and the fixed rate there is the one that equates the two legs in a standard swap contract. So for a CDS, similar, you have fees coming in, and then you get protection in return. And the value of these two, well, this is the fee up here that makes this such that the value of the fee leg is the same as the value of the protection leg. That's going to be the fair CGS spread. Right, so that's the name of the game, is to figure out what is this fair spread in a given model. Any questions or comments on this so far? So the reason that I'm bringing this up in this class is because the process that people used and continue to use to model defaults is this infamous Cox process. So Cox processes, you also call doubly stochastic. You've been around for a long time, way before these CDS contracts were created. This is a mathematical object dating back to the 60s. Cox processes. So this is a way to create this tau. That's the default time. Later on in this course, we're going to be looking at an object called stopping times. For those of you that took the discrete class that I taught 621, you would know what stopping times are. For those of you that have taken the undergraduate 485, you may or may not have seen what stopping times are. Don't worry, we're going to go through stopping times carefully in this class too. But tau is going to be an example of a stopping time. Okay, so Cox processes, this is what will allow you to generate this random variable here. We're just going to call it tau. Okay, so the way that it goes is the input that you have. Input will be, you'll have a diffusion. So let's call that for dyt. So it'll be something like a mu t yt dt plus, there's another mosquito in here, not anymore. Okay, so you have a mu t sigma yt dbt. So that's your diffusion. And another input is going to be a function. So a function lambda goes from r, and then it's going to be positive. And then we need a uniform random variable. It goes over into 0, 1. This is uniform. This is going to be a connection to populus. So that's the buzzword that we'll talk about next time, populus. So we got that, and then I think that's about it. Then what we do is, and we're going to make the assumption here that u and y are independent, right? So u is independent of this stochastic process, yt. Yep, so that's about it. And then we will then look at an object tau. This is going to be the first time where this integral, an exponential of an integral from 0 to t, and then you take the function lambda and you plug it into, you plug y into it, ys ds. This is the first time that this becomes u. So that's the construction. That's what it means to be a Cox process. You take all these ingredients and then you form this random variable tau here. So on a picture, what happens is this here is time. When t is equal to 0, I'm going to get e of 0, right? So I'm going to have it's going to start out here at 1. Like u here is uniform on this interval. This is u of omega is somewhere around here. So say that u of omega is here. This is my u of omega. Now, I'm going to grow a path of y. I'm going to plug that path into lambda. Lambda is positive. Okay, so I'm going to grow a path of y using, say, an Euler scheme, plug it into the lambda, integrate up. And then you see, because lambda is positive, this integral here increases as t increases. So with a minus sign, it decreases. So we have a process here that starts out at 1, and then it goes on. And the first time, this is my e to the minus an integral, and then that path, lambda of ys of omega ds. First time it touches, going to be my tau of omega. So I could have a different path. I'm going to see if I have any more colors. Like if I were to realize a different u, we would move it down or you move it up. These paths here, you could also change. That's how I create my tau. And that's basically what I need in order to price a CDS. Because the CDS contract, what I'll do is I will simulate tau. I'll simulate tau, and then I'll see how many payments I'm going to get. Add them up, price them, right? So there's going to be an interest rate, price them, move them back to time 0. Do the same thing with the protection leg, simulate the tau, see what values it takes. Is it less than if the horizon is 1 year? If it's less than 1 year, well, then you're going to get the payment 1 minus pi. If it's bigger than 1 year, you will get 0. So examples here would include, the first example is if lambda of x is equal to a constant. If I get a constant here, then if I want to solve the equation, e to the minus an integral from 0 to t of lambda ds is equal to u, we can solve this equation here. This is the same thing as saying minus lambda t is equal to log of u. Right, so at this time, this is where I have tau. So I'll put in a tau here. So I'm going to get here that tau is equal to minus 1 over lambda log of u. Does anybody recognize what is this distribution here? Does anybody recognize what this guy is distributed as? How was it? So recall the probability probability transform method. I think this was homework 1. If U is uniform, then if minus 1 of U has a distribution F. So if we took F here to be exponential, so if F is exponential, this is something like 1 minus, what do we get? Let's do this carefully. So if F prime, how is it, exponential? I look at the probability that an exponential is bigger than t. This is e to the minus lambda t. So f of t would be 1 minus. So the inverse function, if I wanted to have x being 1 minus e to the minus lambda t, what's the inverse function I have to solve here for t? So I'll get e to the minus lambda t is equal to 1 minus x. Then I'll do log on both sides. So this is lambda t is equal to log 1 minus x. I get that t is equal to 1 over log 1 minus x. So I get here that f inverse of u, which is equal to minus 1 over log 1 minus 1 over lambda log 1 minus u is exponential. But that is exactly what I have up here. Right, this is exactly what I have up here because this here is uniform. So this one here is exponential. It has exactly the same distribution as if I just use a u. U is uniform 1, 0, 1. 1 minus u is uniform 1, 0, 1. So this one here is exponential. Exponential with parameter lambda positive. So that will be one example of a Cox process. It's going to be the case where tau is an exponential. Makes sense, right? It's a positive time that has a random distribution. We should be able to get the exponential out there. And that's one way to do it. The one we're going to be looking at in the numerics, another example will be, I'll just take yt to be bt, and then lambda would just be the square. And that's my that's the MATLAB example. So let me end the lecture by showing you how straightforward it is to generate these random variables in a Cox setting. Let me switch over to the MATLAB code. Right, so this is my CDS pricer. Can we all see my screen here? This is my little CDS pricer. What are we looking at? So we have pi we have pi up here in the corner. There we go. Pi is up in the corner, so it's not 0.4, it's 0.35 and an interest rate of 4%. Then we're going to be simulating a bunch of paths. So I have 10,000 paths here, and I have discretized the time horizon into 100 time steps. Okay, and so what I'm doing is I'm looking at Brownian motion. This is going to be stored in B, and the integral of lambda is going to be stored in this I lambda. And then I'm interested in stopping times tau. I'm interested in the fees. I'm interested in the recovery rate. And so to simulate it, it's not complicated. I pull a uniform, and then I grow a path of the Brownian motion. I grow a path of the integral, and I put it into the exponential function. So what I do is I sample an increment of the Brownian motion, grow the path of the Brownian motion, I stick it into the integral of lambda with respect to time. So time here is this delta. Okay. Remember, inside the exponential, there will be the integral of lambda with respect to time. So that's what I'm approximating here. And then what happens is I'm interested in these default times. The default time, this is going to happen. This default time is going to happen the first time that it dips down below U. So on the picture, let me switch back to the picture. I'm pulling a U and I'm growing a path up here. The particular example that I'm doing is the one where this here is, so this here is in the MATLAB example. This here is an exponential of an integral from 0 to t. And then what I have here is bs of omega squared ds, right? So this is a ds here. So I'm growing this path and I'm checking for the first time that it dips down below, right? So that means that the previous time it was above and the next time it's below. That's going to give me tau. And I have here, I think I had a 1 year time horizon. I had 100, 1 over the number of time steps. It was equal to 0.01. Let's share the screen again. So that's what is happening here. I had 100 time steps, so 1 divided by 100 is 0.01. I grow the path, and then I check to see if default happens. My default never happens at time 0 because the process inside the exponential, that is 0 at 0, so exponential of 0 is a 1, and U is uniform on 0, 1, so you're not going to get default at time 1. So if there is a default, so there is some m up to those 100 time steps where you dip below, then I update the fee and the recovery. What I do is the fee leg, I'm gonna get whatever the fee rows that I had before, and I just discount back. This is this integral. I'm just discounting $1 back. Same thing for the recovery. If there is a default in the period, then the recovery leg is going to get increased by this 1 minus pi. And of course, if there's no default, I just end up paying the fees. And so I take the mean and the average, and I run it, and see what we get. And you can see it's fairly straightforward. The code is not complicated to do a CDS pricer, and you get a spread here of like 968 basis points, so 9%, 9.7%. And of course, when I change around the underlying stochastic process, if I don't want to have a Brownian motion as my y process, if I don't want to have the square function, Did I use the square function here? Lambda, no, I did not use the square function. I just used a constant. So if you want to use the square function, we just change it around a little bit. If I use the square function, then I'm going to get different numbers over here, of course, but it's a minor change. It's a minor change in the code. Are there any questions or comments? So here is this served to motivate these Cox processes. As you can see in the simulation, it's not complicated to simulate these stopping times. Well, we don't know the stopping times, but there will be stopping times when we move on. It's not difficult to simulate this Y using like a explicit Euler scheme. You just pull these independently and you just grow it, keep track of when it crosses. When it crosses, this is when you have default. And then that will allow you to price a CDS contract. And I'm not kidding when I say that in this period here, this was what you saw on my code. This was seriously what banks used to price deals on CDS contracts in very, very, very large numbers. It was not more complicated than that. It was relatively straightforward code that people use to price these CDS contracts. You use different lambdas, you use different Ys, but the underlying basic structure was some Cox process like the one we have here. Are there any questions or comments? Otherwise, I think this is a good place to call it quits for today. It was a lot longer today than usual. I think there's all that writing we did in the first part. Right, so next time we're going to start here with Heston and Stein, and then we'll now talk about this and we'll tweak it and we'll start looking at copulars next time. This is when we have not just one underlying name, but we have a multiple collection of underlying names. There are office hours tomorrow morning, and if I don't see you there, I hope to see you next week. Are there any questions before we call it quits? Okay, then I'll see you guys either tomorrow or I'll see you on Friday.
Hi, I just wanted to ask about the projects.
Yes.
So if we've kind of like made our decision, do we just tell you before spring break, or how does that work?
Yeah, you can just send me an email and then I'll put it in the I'll create a little file so I can keep track of all the students who has chosen what.
Okay. Should I send in 2 choices just in case that someone chooses? Like I remember that. No, it's fine.
Yeah.
Okay.
So far nobody has chosen anything, so you would be the first one.
Okay. I really want to do the fixed income derivatives one because I did really poorly on a job interview on that, so I thought it's a good opportunity to like learn more about it.
Yeah.
Okay.
That's so nobody did that last year. So this I think this is a great idea. Fixed income is it's a very important area, right? It is a huge outstanding notional in the US.
Okay.
So whatever questions you got in the interview, now will be the chance to straighten them out. And,
Yeah, that's what I thought too. Okay, thank you so much. Yeah, thank you.